Good evening and welcome to this video for the 2018 electricity exam for the 2018 BDSC Botany Down Secondary College mock exam. So for this one, I've linked the paper down in the description below. If you would like to give the paper a try before you watch the video, please click the link in the description and you can try the paper for yourself. But if you just want here to watch the video, so we'll get straight into it. So question 1, Amit's car battery has gone flat. He goes to buy a new one. This new battery has the following rating. So its EMF, its electromotive force is 12.5 volts, and its energy rating is 150 Ah for 10 hours at 12 volts. So this energy rating tells us that the battery can deliver 15 amps of current for 10 hours at a constant terminal voltage of 12 volts. So we know that the terminal voltage is going to be less than the EMF pushing voltage of the battery because some of this EMF will be lost to internal resistance of the battery. So the terminal voltage that's delivered to the external circuit when there's a current flowing in the external circuit is going to be less than the EMF because some of this EMF is lost to the internal resistance. So we know that our terminal voltage is equal to our EMF minus the current flowing in the circuit times the internal resistance. So in this case, we know that the terminal voltage, so the terminal potential of the battery is 12 volts, which means that 0.5 volts is lost to the internal resistance. So we know that 12 equals to 12.5 minus 15 times of our internal resistance. Therefore, 15 times R equals to 0.5. And therefore, if we plug that into our calculator, we will get R equals 0.033 ohms. And that's our final answer, and this should just be an achievable question. So let me verify that. Yes, sorry. Oh no, this is actually a merit level question. Okay, this is actually a merit level question. My mistake. So you can get a merit grade for getting a correct final answer. For an achieved grade, correct formula and V equals 12. Okay, so basically if you having an achieved, it's basically having a correct formula. So having a correct formula here, that will get you an achieved. Question B. Amit's car starter motor has a resistance of 0.04 ohms. The circuit diagram for the starter motor circuit is shown below. How much current will flow through the starter motor when the ignition switch is closed? So we know that when the ignition switch is closed, it's going to be a current flowing through the circuit. So we're going to call this current, we'll say that this current is I1. So we can actually choose to use Kirchhoff's voltage law, so that's energy is conserved in the circuit in order to find out our total current, okay? So in this case, we're going to have our EMF, which is 12.5. And some of this EMF will be lost to the internal resistance, and that's equal to 0.033 times of I1, because the amount lost is dependent on the current flowing in the external circuit. So the bigger the current, the more EMF is lost to the internal resistance, the more heat energy is produced by this internal resistance, so therefore the more energy that's lost. And we also have minus the I1 times of 0.04, that is the energy, that was the voltage across the starter motor, so that's 0.04 times of I1, and we know that equals to 0. So therefore, 12.5 equals 0.033 I1 plus 0.04 I1, therefore 12.5 equals to that equals to 0.073 I1, and therefore if we find out I1, we should get a very, very big current here. So I1 equals to 171.23 amps, but we need to round this one down. Okay, we need to round this down. We probably round it down to probably round it down to 2SF in this case. Okay, I know this 0.04 ohms is 1SF, but in terms of this is 2SF, this is 3SF, it's a bit unclear. I'll probably round it down to 2SF, so that's 170 amps, that's 2SF. So this question, this is just an achieve level question. Okay, you can get achieve for finding out correct answer. Question C. when a mate arrives home, his neighbor John calls him to get his car started as his car battery was also flat. Amit knows that to start a car, a very large current is required to be supplied by the battery, so he connects his new car battery in parallel to John's flat battery. The diagram below shows the circuit diagram of the connections. Calculate the current flowing through the starter motor. So in this case, we're going to be using the Kirchhoff's current law, so that's the conservation of charge around the junction, and we're also going to be using Kirchhoff's voltage law, so that's energy is conserved around the closed loop. So if we label our points here, we can label the edges of our circuit just to get an idea. So we say A, B, C, D, E, and F. So first thing we can do, we can look at, we'll just say look at loop A, B, C, D. And we know that the current is conserved, so charge is conserved, as well as voltage, so energy. So in this case, our positive terminal, so in this case we have we start at this battery here. Okay, so we're going to make one full loop around A, B, C, F. So we're going to start with positive 12.5, okay, assuming that our current is moving this way. So for these kinds of questions, you can just guess, or quote unquote guess, the direction of the current. If you get the direction of the current as a negative value, you'll know that it's actually the positive value in the opposite direction. So for this example, I'll just say that current 1 is flowing in this direction, current 2 is flowing in this direction, and current 3 is running in this direction. I could be wrong, okay, it could, at the end of the day, I2 could come out to be negative, for example, but then we'll know that it's just be positive in the other direction. So in this case, we have positive 12.5, okay, minus the amount lost to the internal resistance, so minus 0.033 times of I1. And we're going to come down, so we're going to go from C to F. So from C to F, we're going to have a voltage drop of 0.2 I2. And we're going to have another voltage drop because we're going against the positive terminal of the battery of 12.4. And we know this is everything is equal to 0. So therefore, we're going to get our equation that's 0.1 equals to 0.033 I1 plus 0.2 I2. So that's our equation number 1. Equation number 2 can be the conservation of charge. That's Kirchhoff's current law. So that's saying that the current flowing into a junction is equal to the current flowing out of a junction. So if we look at junction C here, we have I1 flowing into the junction, and we have I2 and I3 flowing out of the junction. So therefore, Kirchhoff's current law says that charge is conserved. So Kirchhoff's current law, so we can say I1 equals to I2 plus I3. So that can be our equation number 2. In terms of our equation number 3, we can either look at loops C, D, E, F, or we can look at A, B, C, D, E, F, A. In this case, it doesn't really matter which loop you choose. For this specific example, I'll just say we'll look at A, B, C, D, E, A. So in this case, okay, we're going to run in the same direction. We're going to start from this battery here. So we have loop A, B, C, D, E, F, A. And we're going to start with positive 12.5, and some of that's going to be lost to the internal resistance, so a voltage drop of 0.033 times of I1. And we're going to travel along, so we're going to go from D to E. So from D to E, we're going to have another voltage drop of 0.04 times of I3. And we know that this is equal to 0. Okay, so there's nothing else, and we come back and there's a full loop. So this is equal to 0. So therefore, 12.5 equals to 0.033 I1 plus 0.04 I3. Alright, so in this case, we have our equation 1, that's 0.1 equals to 0.033 I1 plus 0.2 I2. And for our equation number 3, we can call this equation 3. We have 12.5 equals to 0.033 I1 plus 0.04 I3. So for these types of questions, we're just solving simultaneous equations. Okay, so in this case, we can look to eliminate a variable. So in this case, we can say that I1 equals to I2 plus I3. So 0.1 equals to 0.033 times of I2 plus I3. We're looking at equation 1 right now. And plus 0.2 I2. So if we simplify this one a little bit, we get 0.1. That equals to 0.033 I2 plus 0.033 I3 plus 0.2 I2. Alright, so we're going to get 0.1 equals to 0.1 0.233I2 plus 0.033I3. For equation number 3, we can substitute I1 equals to I2 plus I3, again, like we did in equation number 1. So we can call this equation number 4. And for equation number 5, we can say that 12.5 equals to 0.033 times I1 plus I2 plus 0.04I3. So therefore, 12.5 equals to 0.033I1 plus 0.033I2 plus 0.04I3. Okay, so we're going to get 12.5 equals to 0.073I1, sorry, not I1, I3, plus 0.033I2. So now we have our equation number 5 and our equation number 4, both are in terms of I2 and I3. So now we can actually just do a simultaneous equation. So at this point, like, since it's all very mathematical, okay, we can keep going and cancel out the variables, but in the exam you only have 1 hour. So when we get to this stage, I'll just go to your calculator, you go to simultaneous equations, okay, and we're going to simultaneous equations. Number of unknowns is 2, and we're just going to enter in these values, okay? So okay, so now we're getting some answers here, okay? So now we have I3 coming up to be 182.73 amps, and I2 is coming out to be negative 25.45 amps. So remember, as I was saying at the start of the question, if we're getting a negative answer for our I2, that means that this is actually not in this direction, it's actually in this direction. It's actually flowing upwards from F to C. So that's just something we can note down. So I2 is actually flowing from point C to point F. But the question was asking us to calculate the current flowing through the starter motor. That's actually just I3, which we've already done. So there's actually no more further steps we need to do. For this question, I would round this one down to... So once again, the significant figures here is not very clear, but I'll just probably go down to 2SF. Okay, so I'll just say I3 equals to 180 amps. That's in 2SF. Yeah, so the mark schedule here, they've done it in 4SF, but typically in the exam, you're supposed to round down to the lowest SF given by the examiner. So in this case, just don't really worry about it. So in this case, we got our answer correctly. Okay, so the correct value of I3, that'll get us an excellence grade. To get a merit grade, you need any 2 equations correct, so that's the Kirchhoff equations. So like I said, these equation 1, equation 2, and equation 3, if you can get just 2 of these equations, okay, just any 2 out of 3, that will get you a merit. And to get an achieved, you can just get any 1 out of 3 of these equations, and then you get it achieved. Alright, and that's it for that question. So when returning home, John switches on the headlights of his car and then turns on the ignition, so closes the ignition switch to start the car. John notices that when he turns the ignition on to start the car's headlights go dim. The diagram shows the circuit diagram of the connections. Without doing any further calculations, explain why the car's headlights get dim when John turns on the ignition to start the car. So we see that the car's headlights goes dim, so we can immediately link the going dim to lower brightness, and we can link the lower brightness to a decreasing power. And a decreasing power, that's depending on the current and the voltage. Therefore, we know that one or both of these values have dropped in these headlights. So basically, when we are turning on this, when we close the switch, we know from the previous question that the starter motor is requiring a very large current to get started. Okay, very large current is needed to supply to the starter motor. And we know that once the starter motor is connected, we have a 3-way parallel branch. And assuming that the resistance of the headlights was greater than 0.4 ohms, the total resistance of the circuit will drop down to 0.04 ohms, or it will be less than 0.04 ohms. So in this case, it's going to be a very, very large current that's drawn from the battery. Very large current drawn from the battery, and therefore, because we have our internal resistance that didn't change, because there's more current being supplied to the external circuit, therefore there's actually more energy that's lost to the internal resistance. So more of that potential energy is being transferred into heat energy lost in the internal resistance. Hence, there's actually less terminal voltage that's being able to be supplied to the external circuit, which means that these bulbs will have a lower potential, and therefore they're going to have a decreasing brightness. So those are the points we need to link together, okay? So quite a bit we need to get through here. So okay, so we can say that when red pen. So we can say when the when the ignition switch is closed, you can say that the total resistance is now less than 0.4 ohms. 0.04 ohms, 0.04 ohms. This means that a very large current will be drawn, very large. So you can link this one to V equals to IR, and we know that the resistance is decreased, so therefore current must increase, so I is proportional to 1 over R. Therefore, more potential energy. So more potential energy is lost to the internal resistance as heat. So more potential as is more current delivered to the external circuit. So as there is more current delivered to the external circuit. So you can say that E equals to, so the terminal voltage equals to the EMF minus the internal resistance times the current. So therefore, as current increases, E stays the same. E stays the same. Therefore, the voltage supplied, or the potential difference supplied, doesn't matter, or therefore the voltage supplied to the external circuit decreases. Okay, so the voltage supplied into the external circuit decreases as the so you can say that the bulbs will have a lower potential, than before. So then before the ignition switch was closed than before. And you can link that to P equals to IV, so it would be hence as P equals to IV, you can say that the so as P is proportional to V, the power decreases, and therefore the brightness will decrease. And you can link that one to the bulbs going dim. So bulbs go dim. Alright, so that's all we really need to link for this question. Okay, so for this question, we need to link 7 bullet points. So the first bullet point is when the ignition switch is closed, the total resistance drops below 0.04 ohms. Therefore, a large current is now drawn from the battery. This large current creates a large voltage drop across the internal resistance, or in case we said that the more potential energy is lost to the internal resistance, that's fine as well. So we can say that since the terminal voltage is the EMF minus the potential energy lost to the internal resistance, therefore the terminal voltage will decrease. And you can say that so that's bullet point number that was bullet point number 5. Bullet point number 6, So you can say that V proportional to I, so therefore the voltage across the bulbs will also decrease, therefore the power will decrease. And therefore, since power is proportional to voltage, so P equals to VI, therefore the power decreases and the brightness will decrease as well. So linking all 7 of those bullet points, that will get you an excellence grade. To get a merit, you need any 4 of those bullet points. So of those 4 bullet points I just said, so 4 out of 7 will get you a merit. 2 out of 7 will get you an achieved. Right, so for question number 2. Josh is trying to design a capacitor to do an experiment on how charges can be stored on 2 conducting plates. Question A. Josh uses 2 pieces of steel that's 2.35 times 10 to the power of -3 meters apart to create his capacitor. These pieces of steel are 0.2 meters long and 0.3 meters wide. The permittivity of free space is 8.84 times 10 to the power of -12 farads per meter. Calculate the capacitance of the capacitor. So the capacitance of the capacitor really depends on the physical properties of the capacitor and the physical setup. So our formula for that one is capacitance equals to permittivity of free space multiplied by our dielectric constant multiplied by the overlapping area of the plates divided by the distance of separation. So in this case, we have all our information we really need. So that's C equals to 2.53. Oh, sorry, not what am I saying? 8.84, that's our permittivity of free space, times 10 to the power of -12. In this case, we can assume that our dielectric constant is 1, since they didn't give us that information, so we just assume that our dielectric constant is 1. And we have our area. So our area is equal to the length times width of the capacitor, so that's 0.3 times 0.2 divided by the distance of separation, which is given as 2.35 times 10 to the power of -3. All right. Right, we should have got our answer as capacitance equals to 2.26 times 10 to the power of -10 farads. That one should be our final answer for that question. 2.26 times 10 to the power of -10, that is correct answer. So that will get us an achieved grade for a correct answer. Describe 3 changes Josh can make to increase the capacitance of his capacitor. So for these, like how you can increase ones, just write out the formula to start with so you know exactly what's being dealt with. So E0 times ER times A over D. So in this case, you can't really change the permittivity of free space. That's a fixed constant, so you can ignore that one. So as you can see, there's 3 variables left: the dielectric constant, the area of the plate, and the distance of separation. So the first point, you can say that we could add a dielectric material between the plates. It will cause a polarization, therefore more charge can be stored on the plates, increasing the capacitance. You can say that we can also increase the area or overlapping area of the plates, so therefore likewise more charge can be stored. Or you can say that we're going to decrease the distance between the capacitors, therefore there's a stronger attraction force between the plates, therefore increasing the capacitance. Okay, so for these ones, you can just say so number 1, we can add a dielectric dielectric material between the plates. Okay, so we can say that C proportional to ER. For number 2, we can say that we can increase the overlapping area, so we can increase the overlapping area of the 2 plates. So that's our C proportional to A, and we say for number 3, we can decrease the separation between the plates. So that's our C is proportional to 1 over D. And that's really what we need to do, okay? So we just need to mention, just like what I've done, just bullet point these three methods. You don't really have to go into too much detail for this question. So for this question, you can actually just get a merit offhand just by listing these 3 ways to increase the capacitance. For an achieved, you can get 2 out of 3. So 2 out of 3 is an achieved, 3 out of 3 is a merit. Right, so question C. Yeah, question C. Josh connects a 14.4 volt DC power supply and a 20 ohm resistor in series to his capacitor. By calculating the time constant, plot a charge versus time curve for discharging capacitor, include at least 3 plotted points. Use the space at the bottom of this page for calculations. So in this case, we're going to be using a discharging capacitor, meaning that it's initially charged. So therefore, when we discharge it, the amount of charge on the plate is going to decrease. Therefore, its voltage is also going to decrease, and it's going to follow an exponential decay. Okay, so this graph should be an exponential decay. So exponential decay, if we just want to work a quick sketch, that looks something like this. So exponential decay. So we know about the time constant. So first we're going to work out the time constant. The time constant for the discharging capacitor, that's equal to so the time constant for our discharging capacitor, that's equal to the resistance in the circuit times the capacitance of the capacitor. So that's R times C. So in this case, I believe they should have given both values. So R is 20, and I assume that the capacitance was the value that we calculated in part A. They should have made that a bit more clear, but it's okay. So time constant equals to 2.26 times 10 to the power of negative 10. That was our calculated capacitance in A multiplied by 20. Okay, so what is this? That's 2.26 times 10 to the power of negative 10 times 20 times 10 to the power of negative 9 seconds. Okay, it's a very, very small time constant. So we're going to have to scale down our graph. Effectively. Okay. All right. So in terms of drawing our graph, we can. I'm gonna get some lines here. We can use a straight line. That'd be better. Okay. I'm going to add another line here. So another line for our x-axis. So our x-axis is obviously just going to be our time. Okay, so this is time in seconds. Okay, so plot a charge versus time. Okay, so obviously, so this is charge. Okay, so this is charge over time. Okay, so first we have to find out our initial charge. Okay, so our initial charge on the capacitor, that's charge equals to C times V. Initially, because the capacitor is fully charged, the potential of the capacitor is equal to the DC power supply. That's 14.4 volts, because it's going to have so when the capacitor is charging, it's going to build up charge, and eventually no more charge can flow in the DC circuit, because the pushing voltage of the capacitor is equal to the pushing power of the DC power supply. They are in opposite directions, hence they'll cancel each other out, so there's no more flow of charge onto the capacitor. Therefore, that's its maximum pushing voltage there. Okay, so therefore the pushing voltage of the capacitor will be equal to the DC power supply. In this case, it's 14.4 volts. So therefore, Q equals to 2.26 times 10 to the power of negative 10 multiplied by our V, which is 14.4. Should give us an answer of 3.2544 times 10 to the power of negative 9 coulombs. Okay, so for this one, I think what we could do here is we can say this is charge, but this is in terms of 1 times 10 to the power of negative 9 coulombs. And for the time, we can label this one as 1 times 10 to the power of negative 9 seconds. So that might make our life a bit easier, so we can just ignore this times 10 to the power of negative 9 when we're plotting our graph. Looking at these values of 4.5, we can make each gap here, we can make it 0.5 to make this graph a bit more spread out. Sorry, actually that's a bad idea. Sorry, because only after about five time constants, it's considered to be fully discharged. So it's considered to be fully discharged, but technically it's not fully discharged, because it's never going to be fully discharged, because it's an exponential decay. But after 5 time constants, it's considered to be fully discharged. So if we did 4.52 times 5. So that's about 22.6. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, so what we could do here, we can make this, so we can make it in gaps of 2, might be a bit better. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, and 22. And this is 24. And for in terms of our charge, we know that our maximum charge is 3.25 for 4 times 10 power negative 9. So therefore, we can make each gap here, we can just make it, we can make it 0.25 actually. We have enough space, so just to space out our graph a little bit better, we can do this. Ooh, have enough space? Yeah, I think we do. Yeah, barely enough space, but that's good. And we have 3.50 at the top here. Okay. So our charge is going to start somewhere there. That's when time equals 0. So that's the maximum number. That's the maximum amount of charge. But after some time, it's going to start discharging. Okay, and it's going to discharge through the 20 ohm resistor. And its charge on the plates is going to start decreasing. It's going to go as an exponential decay. So in this case, we know that the amount of charge decreases by 63% per time constant. Or we can just remember the formula that C equals to the C maximum times e to the power of negative time over time constant. So for this formula, we can actually prove this one using calculus, but I won't go there. So in this case, if you just remember this formula, it saves you a lot of time, because I see that a lot of people, what they tend to do is they just tend to keep decreasing by 0.63 each time, and they have to do it for like 3 or 4 times. They just go, what they would do is just they would plug numbers into the calculator, and then they would go, oh, okay, so I have to plug all those numbers back and then times by 0.63, and then times, it takes a lot longer, so it takes more time, and then it makes it more likely for you to mess up. That's not good, okay? So for this one, it's much more easy. So after 1 time constant, C equals to the C maximum times e to the power negative 1. After 2 times constants, it'll just be e to the power negative 2. For 3 time constants, it'll just be C maximum times e to the power negative 3. So very simple to use the formula, okay? So very, very simple here. So after 1 time constant, so C after 1 time constant, that equals to a maximum charge, which is our calculator, 3.2544 times 10 to the power negative 9. I'll just write a C maximum because I don't want to write the whole number, it's too long, times e to the power negative 1, okay? So looking at this one, we should just get 3.2544 times 10 to the power 9 times by e to the power negative 1. Right, it's a C maximum. Well, sorry, not C maximum. C after 1 time constant. That equals to 1.197 times 10 to the power negative 9 coulombs. So let's plot that one into our graph. So we know that 1 time constant is 4.5 times 10 to the power negative 9. That's somewhere here, okay? So I'm not going to be too precise here. So that's somewhere there. And it's 1.197 times 10 to the power negative 9 coulombs. So therefore, it should be somewhere here. Right, so that's our point number 1. So after 2 time constants, we're just going to say maximum times e to the power negative 2. So 3.2544 times 10 to the power negative 9 multiplied by e to the power negative 2. So this gives us 4.404 times 10 to the power negative 10 coulombs. Okay, so we're actually going to be down at the 0.4 section here. So 4.52 times 2 is about 9, so we're going to be somewhere here after 2 time constants, and going to be somewhere here. Okay. Oh wait, did I do that one right? Seems off. So 4.4 times 10 to the power negative 10, so 0.44 should be right, but looks funny. Did I do something wrong here? Let me try that again. Sorry guys, hold up. Let me try this one again because the graph looks a bit too steep. I might have done something wrong here. E to the power of negative 1. Let's try that one again. 3.25. Okay, so I didn't actually make any mistake. It doesn't look like it did. Just must be let's see, just the scale isn't that great, but it's okay. We'll just, so C after three time constants as our final point. So that's 3.2544 times 10 to the power of negative 9 times of e to the power of negative 3. So 3.25. This one is 1.62 times 10 to the power of negative 10 coulombs. So that one's going to be even lower. So 4.52 times 3 is about 13.5-ish. So it should be somewhere here. And our graph should be somewhere there. Okay. So now we can just draw in the points. Okay, it'll be very hard for me to draw the line on iPad, but just try my best here. So, sorry, it doesn't look very good, but yeah, sorry, it doesn't look very good, but I hope you can get the idea. So in the exam, it'll be a lot easier because it's on paper, but for me, it's a bit hard right now to draw the graph. But it should look something like this. Okay, it should very flatten out and should approach 0 coulombs. All right, and that's good formula to remember. It saves you a lot of time and decreases your time to make a mistake. So this is when, in terms of the formulas, this is when something's decreasing. Like it could be charge, it could be current, it could be voltage. When it's decreasing, you can just remember it's e to the power negative t over time constant. Okay. In terms of when it's going upwards, so let's say it's a charging capacitor, it's simply just going to be, for example, C equals to the C maximum times 1 minus e to the power of negative t over. Sorry, negative t over t. So that would be the formula if it's going upwards. Okay, so you can just remember these formulas. It makes your life a lot easier. Okay, it makes your life a lot more easier because you don't actually have to plug the numbers in individually, and like you don't really have to plug numbers in individually, and like it takes, like I said, it takes a lot longer and a lot higher chance you make a mistake. Okay, so those are the two formulas. So this is when the graph looks like this, and this is when the graph looks like this, the one we just did. Okay, so this is decreasing. So just remember. Okay, so all we need to do is just remember these formulas. Okay, very helpful on the day, very helpful. Okay, so decreasing is just e to the power negative t over t of the time constant. For increasing, there's a 1 minus, okay? So just remember that one. Okay. All right, in terms of grading for this question, okay, it's actually an excellence level question, okay? So for an excellence, you need to calculate correct time constant. Correct time constant, that's 1 point. You need to have a correct initial charge, and so correct initial charge, correctly labeled 3 points. Okay, so you calculated 3 points. I mean, we could have labeled it on the graph. We should have labeled it on the graph, but like, you know, we didn't do that. But we could just, if we wanted to label the graph, we could just label the values we found. So, time at 1 constant is 1.197 times 10 to the power negative 9, and etc. And for the third point, we need a correct exponential decay graph shape drawn. So correct exponential decay shape drawn, that's 0.3. For an excellence, you need all 3 points. Okay, so 3 out of 3 is an excellence. To get a merit, you need 2 of those points. So 2 out of 3 is a merit. 1 out of 3 will be an achieved. Okay, so Josh tries to double the capacitance in the circuit by connecting a second identical capacitor. Sketch the circuit diagram for this combination of the two capacitors that will achieve this, and explain whether this will take more, less, or the same amount of time for the two capacitors to get fully charged. So when we add capacitors in parallel, that is when we actually increase the capacitance. That's when we add the capacitance. So we're going to have to connect these capacitors in a parallel circuit. So sketch the circuit diagram. So we have our battery. We have our capacitor number 1, and we're going to have our capacitor number 2. Okay, so that's just a circuit diagram. That's very, very simple. This has a capacitance, and second one has a capacitance as well. So this is CT equals to total capacitance equal to C plus C, which equals to 2C. Alright, so now we're going to answer the question. So I sketch a circuit diagram for the combination of the two capacitors that will achieve this, and explain whether this will take more, less, or the same amount of time to get fully charged. Okay, so basically we so for this question, so looking at this one, so explain. Alright, so in this case, we're going to have a battery, and it's going to be charging these capacitors, very similar to how the battery will be charging one capacitor, but in this case, it will be a parallel. So in this case, it would actually take longer, because the reason it's going to take longer is because there's two capacitors now, which means that the total capacitance equals to 2 times the original capacitance. And that means because time constant equals to 2 times of C times of R, and therefore the time constant is going to be doubled. Therefore, because the time constant is doubled, it's going to take 2 times as long in order to get fully charged. And that's because we can actually just redraw the circuit diagram. What the circuit diagram really looks like is just this one. It's basically the same thing, but this is 2 times of C. It's basically the same thing, because we have two capacitors in parallel, which is the same as saying the total capacitance equals to C plus C, which is 2 times of capacitance. So we're saying that it's just one capacitor connected in series, okay? So in this case, I'm going to say that it will take longer. It will take longer for the capacitors to be fully charged because the total capacitance in the circuit has doubled. The total capacitance of the circuit has doubled. So you can say this means that the time constant will also double. So time constant will also, and you can say the time constant equals to R times of C. Then it will take twice as long. It will take 2 times as long to reach, to get the capacitors fully charged. Sorry, get the capacitors fully charged. Right, and that's really all we need to say for this question, okay? And so, okay, so for this question, you need a correct circuit diagram, so that's very simple there. And we also need to have, so time constant doubles, therefore it takes twice as long. That's all we really need, so both of those points will get you a merit. To get an achieved, you can have a correct circuit diagram, or you can just say that the time constant will double, therefore they will take twice as long for the capacitors to get fully charged, okay? So 1 out of 2 will get you an achieved. Alright, so for question 3, I'll leave it to a separate video because this one's getting a bit long. Okay, so I hope you enjoyed this video. If you did, please drop me a like. If you have any comments or feedback, please leave it down in the comments below. And I